everyone. So today I'm going to be doing the course questions for AP Chemistry Chapter 1. Now it's really easy, but Chapter 1, like especially, it's not that hard. And since there's no course practice, the only things you could study are the book. And this year, since there's no notes, please do read the book. You need to read the book, actually, because she does get questions from the book. And you should solve see the CQDs I'm solving now. And you should do AP Classroom past paper questions for the written part especially. Anyways, let's start. So, an experiment was conducted to deduce the charges and mass of subatomic particles of atoms by passing the subatomic particles through a constant electric field. Why did beam A deflect the most? Now, as you can see, here's a positive beam, or the plate, and here's a negative plate. So if beam A is going towards the positive plate, it has to be electrons, because electrons are negatively charged and they're attracted by the positive plate. Now, we know that beam A is electrons, and electrons have a mass of 1/1836. So they are the lightest particle. That's why they deflect the most, because they're electrons and the lightest. I won't write all the answers. Lightest. Now, why does beam B not deflect at all? It's because they are neutrons and they have no charge, so they're not attracted to anything. They are neutral. They're not affected at all. Now, electrons, their symbol is E-, neutrons is N0, protons is P+, the mass is 1/1836, the mass of neutrons is 1, and the mass of protons is always 1. The charge of an electron is -1, the charge of a neutron is 0, and the charge of a proton is +1. These are all questions you should just memorize because they come every single time. Now label the positive plate, the negative plate, and the subatomic particles A and B in the above diagram. Okay, so B is obviously neutrons, and if these are protons, they must be attracted to the negative plate. So if this is the negative plate, then this must be the positive plate, and the thing that's attracted by the positive plate has to be negative charges, aka electrons. That's it for this question. We're done with question 1. Let's move on to question 2. An isotope of rubidium has 85 nucleons and 37 protons. Nucleons are basically basically neutrons and protons. So, give the atomic symbol. Now, to write an atomic symbol, you have to write your chemical symbol. So, in this case, it's Rb. Then, you need to write the mass number, or aka the number of nucleons. The mass number is the number of neutrons plus protons. So, then, if they gave us nucleons straight away, you could directly put 85 up. And always down is the number of protons, or the atomic number. So the number of protons is always down, the number of protons plus neutrons is always up. And if it is an atom, the number of electrons is equal to the number of protons. And this number of the number of nucleons is called A, and the number of protons is called Z. So yeah. Give the atomic symbol for, this is the atomic symbol. Now give the number of neutrons. It's 85 minus 37 nucleons. So 85 minus 37 it equals to it's equal to 48. Now, a rubidium ion atom forms a rubidium ion. Choose the number of electrons in the ion. Now, you need to know one thing. If you have, it's like I said, if it's an atom, it's like the protons. But here you have an ion, and the ion is +1. This means +1. If it's +1, it means it has gained an electron. If it has gained an electron, it means you need, if it's +1, it has lost an electron. Because if it's -1, it means it has extra -1 charge. If it's +1, it has -1, like it's missing an electron, so it's plus. It has an extra positive charge. So here it's +1, so you subtract 1 to get the number of electrons, 36. Complete the table. Okay, so number of protons, it's always like the bottom number. Always. So it's always the number Z. So it's 56 and 17. Here the number of neutrons is always A minus Z. So it's 80 minus 35, which is 45. And here it's 137 minus 56, which is 81. And here it is 35 minus 17, which is 18. Now the number of electrons in this one is, since it's an atom, not an ion, is the same as the number of protons, so 35. Now the number of electrons in Ba2 plus is 56 minus 2. Because remember what I said? It is, since Ba has lost 2 electrons, you need to subtract. Now Cl is Cl minus, so it has gained an electron, so it is 17 plus 1, 18. Now, americium, or however the hell it's pronounced, is a synthetic radioactive chemical element with the symbol Am. Its atomic number is 95 and its mass number is 243. Draw the atomic symbol, so it's just Am with, to the left of it, 243, and down here it is 95. Give the nuclear relative charge of Am. Nuclear relative charge means the charge of its nucleus. Now in the nucleus we have, like here in the nucleus, you have positive, or like protons and neutrons. Since neutrons have no charge, it is equal to the charge of the number of protons. Since we have 95 protons, it is plus 95. Explain one similarity and difference between the isotopes. Isotopes are two elements that have the same number of proton, same electric configuration, same number of electrons, but they have different number of neutrons. So one similarity is same protons, different neutrons. That's the symbol, and like that's a, yeah. And they have, yeah, and they have different physical properties, by the way. Since because they have different number of neutrons, they can't have the same physical properties, but they're also gonna have the same chemical properties. That's the one in the Marx scheme. They have the same chemical properties because they have the same electronic configuration and protons, but different physical properties because they have different neutrons. Now give the isotope of give an isotope of Am's chemical symbol. So the number down will never change. If they change, it's a different element. And the number on top, since here it's 243, you cannot have 243. You could have 240 anything but 3. So you could put 242, you could put 244, 245, 241, anything but 243. Now, naturally occurring lithium is composed of two isotopes. The average atomic mass of lithium is 6.9. Calculate the percentage abundance of each isotope. Now, to calculate the percentage abundance, we have to first see there. Now whenever you have a compound, it's made out of more than one. So how do we calculate? It's the mass times percentage abundance plus mass 2 times percentage abundance 2 all over 100. And if you have more than 2, you could add more than 2, but in our case here we only have 2. Now the mass of lithium is is given here 6 and 7, right? So it is 6 times we're gonna call it x, and M2 is gonna be 7 times, now you're gonna say let's name it y. We can't. Now what is x? X is out of 100. It's the percent out of 100, because the percentage is out of 100. So if one of them has x, the other one must have 100 minus x. Now what do? We do this is all equal to 6.9. So now it's 600. Oh no, what did I do? So 690, I switch them up, equals 6x plus 7 into 100 minus x. Now what we do is we can distribute. 690 equals 6x plus 700 minus x. So it's 5x equals to negative, wait, no, not negative. No, actually negative. I forgot to distribute the 7 into the x, so it's minus 7x, yeah. So it's negative 5x, or negative x, because now it's not plus anymore. Negative x equals negative 10, so x equals 10. Now you have to go back to your equation, the one you wrote. You've looked for the one with x. You gave x to the one that has a mass of 6. So the percentage abundance of the one with the mass 6 is equal to 10%, and the one with the percentage abundance of the mass 7 is equal to 90%. And that's it. Now next question. Here you have a mass spectrum. Deduce the number of isotopes. To know the number of isotopes, it's the number of lines. So here you have 2 isotopes because 2 lines. Now calculate the relative average mass. So we're gonna do 35 times 75.78 into plus 37 times 24.24 all over 100. Put this into your calculator, you're gonna get 35.5. Now when you go down to your periodic table, you need to use your periodic table. Find the element with the mass of 35.5 or 36 or 35. Yani it's most likely gonna be one of them. It's now when you go and you see it's chlorine. Identify the element means you could either give its name or its element symbol, but usually they tell you give its symbol or give us its name. They never just say identify. Most, if they do just say in the identify, give the name. The surface of sodium metal is struck by electromagnetic radiation of increasing energy. Electrons they emit energy of the photons is 3.76 times 10 power negative 19 joules. Deduce the color of the light used by the electrons to eject. Okay, that's the only part, that's the question itself. So we have to memorize 2 equations. Three equations. Now let's go with the basic equations. The basic equation is what's it called? Speed of light equals to C equals lambda, which is the wavelength, times V with a squiggle, which is the frequency. So this is speed of light in vacuum, and it is always equal to 3 times 10 power 8 or 2.99 times 10 power 8, depends on what they give you. This is the wavelength. And this is frequency. There's a second equation, which is frequency equals, or no, energy equals Planck's constant times frequency. Now, the equation, another equation, which is the mixture of these two equations when we do not have frequency, is H equals Hc over wavelength. H is Planck's constant, which is equal to 6.626 times 10 power negative 34. And we already said that, yeah, C is equal to 3, yeah. So now, they gave us the energy. We do not have a frequency, and they want the wavelength. So we have to use this equation. So it's energy, which is 3.676 times 10 power negative 19 equals Planck's constant, which is 6.626 times 10 power negative 34. I'll write it back here. H equals Hc over wavelength, lambda. And then it is times 3 times 10 power 8 all over the wavelength which we are trying to find. If you have a calculator that is, it has a calc button, just do it there. Then if you don't, just do these two numbers divided by this number, and then you will get 529, or like you're gonna get 5.29 times 10 power negative 7 meters, which is equal to 529 nanometers, because nano is times 10 to the power of 9, negative 9. Well, but since you're going from smaller or from bigger number to smaller number, you times by 10 power 9, and it's gonna be 729 anyways nanometers. So now we need to go back and look what color is between the range of 729 nanometers. This one definitely not. Here it is 585 is higher than 729, so it can't be this. Again, 575 is also higher. 491 to 575. This is the one that fits the range, so the color of our light is green. Now we're gonna move on to question 8, which is a grid question. So it's very important. Calculate the energy of a photon whose wavelength is, so we have energy and we have wavelength, and they gave us these two information. Oh, we don't have energy, sorry. They said calculate the energy, and we already have the wavelength. So we just apply the same rule we used up, which is E equals Hc over lambda. Since we do not have frequency, we cannot apply E equals H frequency. So what's it called? So yeah, now we do 6.626 times 10 power negative 34 times 3 times 10 power 8 all over, oh yeah, it's PM. P is times 10 to the power of, it's pico, which is 10 to the power of negative 12. So memorize it. 558 times 10 power negative 12. And if it's FM, it's times 10 power negative 15. In case she decides to test our converting abilities in the exam. Anyways, put this into your calculator. You should get an answer of 3.55 times 10 power negative 16 joules. And energy is always in joules, so make sure you put it in joules. Now, state the maximum number of electrons that can occupy the 5th energy level. When we're talking about electrons and energy levels, there's a formula. If you want the maximum number of orbitals in an energy level, so max orbitals, it is n, which is the energy level squared. But max electrons in these orbitals, it is 2n squared. So they want the maximum number of electrons. So we use the second equation in the 5th energy level. So we just replace it by 5, n by 5. So 5 squared is 25 times 2, so it is 50. Now look, when we have this shape, no, it is a, what's it called? This shape is s orbital. This shape is, it looks like a dumbbell. If it looks like a dumbbell, it is the p orbital. And if it looks like a 4-leaf clover, or this, it is the d orbital. And if it is a weird complex shape, like if it's a weird 3D complex shape, it's the f orbital. I don't think they're ever gonna ask us it though. Now, what's the maximum number of electrons that can be found in a d subshell? You're gonna say, okay, we apply one of these formulas. No, we cannot, because this is a subshell. We're talking about the d subshell, not like the energy level d. So the d subshell can fit maximum of, memorize it actually. So the s can fit maximum 2 electrons, p can fit maximum 6, d can fit maximum of 10, and f can fit maximum of 14. And s has one house, or like it's in, when we write SPDF, it has, s is 1 block, p is 3, d has 5, f has 7. These are all information you should memorize. So in the d subshell, we have 10 electrons. What's the maximum number of orbitals that can be found on the 4th energy level? We said this is the equation, so it's 4 squared, which equals to 16. Now, what is the meaning of degenerate orbitals? Degenerate orbitals are orbitals that have the same energy level. They are orbitals in the same subshell, and energy level. Degenerate orbitals are orbitals that have the same exact energy. Now, which of the following pairs are degenerate orbitals? Now, to have, we said same subshell and energy level. So they all have to start with the same number. And yeah, they all need to have the same letter. So these 3 all start with the same letter or number and number. So this is PZ, PX, and PY. It's supposed to be PZ, but they didn't write the Z. But anyways, since they have the same energy level and they're part of the p subshell, they are degenerate orbitals. But you're gonna say s has the same number of that, but they're in the same energy level, but they're different sub-levels. S is different than p. And wait a minute. Oh wait. For a minute I thought this was a typo. It's only these two, because this is not, it doesn't have a name. If it's 3pz, then it's a degenerate orbital with them. But if it's just 3p, it's not a degenerate orbital, so it can't be these two, because they are in the same energy level but in different sub-levels. And these cannot be, because they start with different principal energy levels. Now, for question 14, it's asking us to draw the orbital notation of the following elements. Now, whenever we see a question asking us for orbital notation, we do first one thing, which is we write down electronic configuration in SPDF. You're gonna say, okay, I don't know how to do that. It's fine. So we use something called the backwards method. So it's, you go backwards twice. You're gonna say, what do you mean you go backwards twice? It's S, S, then P, S, P, S. Then it is D, P, S, D, P, S. Then it is F, D, P, S, F, D, P, S. And that's how you write anything for the entire periodic table. Now, S always has a subscript or superscript of 2, or exponent of 2. P always 6, S2, P6, S2. D always has 10. Now, when I say always has, I mean when it's full. When it is not full, let's say like you can't fill it up, it can have 5 or 4, but D has like 2 exceptions, which I will mention in a bit. P6, whatever. Now, S starts with 1, then 2. P starts with 2. There's no 1P. It's only 2P. And there's no 2D. There's only 3D. And F starts with 4. There's no 1, 2, or 3F. And here it's 14. And whatever. You get the idea. Now, here you have 7 electrons. So we need to count the number of electrons to be able to do it. So it's 1s2, 2s2, 2p. Now 1s2 means you have 2 electrons. You need to add the number of electrons. So now we have 4. You add them. So till now we have 4. Then 2p, 3, because you can only fit you can only fit 3 in the last one. Now we have 2 plus 2, which is 4, plus 3, which is 7. We have enough. Now to draw them. The S only has 1 room in its house. And then to draw it, it's always arrow up, arrow down. Next one. Arrow up, arrow down. Now P, I already told you above, it has 3 rooms. So it is up, up, up. Now, you're gonna say, why did you do 3 ups? Why didn't you do up, down, then up, and whatever? Because there's a principle called Pauli. Pauli is a different law. I'll tell you all 3 laws now. It's a law called Hund's law, or Hund's rule. The orbitals of equal energy are first occupied by the maximum number of unpaired electrons having the same spin. So you must always do up, up, up. Then you are allowed to do down, down, down. But here we only have 3 in P, so we cannot continue. This is it. Now for beryllium, it's 1s2, and now we have 2s2, and that's 4. That you're done. Now it's up, down. You're gonna say, why is it up, down? It's because of the Pauli exclusion principle. The Pauli exclusion principle states that each atomic orbital can be occupied by a maximum number of 2 electrons having opposite spin. Why opposite spin? It's because they don't repel each other. If they're spinning in the same direction, or if they're spinning like not opposite ways, they're gonna repel each other. They won't spin together. And we have one more principle called the Aufbau principle, states that an electron in an atom tends to have the lowest possible energy arrangement. So let's say you have an atom, it cannot start from 2p6, or you can't fill out 2p before filling out 2s. It always has to go from lowest to biggest. So now we have 1s2, and this is 2s2. Now Mg is 12. So it's 1s2, 2s2, 2p6, till now we have 10. And 2 or 3s2. And that's it for Mg. I'm gonna draw it here in red. It is 1 1s2, so up down, 2s2, up down, 2p6. Now when you're drawing 2p, it's like I told you, since they can't repel each other, it's up, 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 down, down, down. Then we can move on to 3s2, which is up, down. Now Al, I'm gonna write down here, it's 1s2, 2s2, 2p6, 3s2, and 2p and 3p1. So it's the same exact thing as Mg. Actually, I'm gonna add to the Mg one. The one in blue is the addition for what's it called? Aluminium. So aluminium has an extra p, and it only has one electron in this p, and that's it. That's how you draw aluminium. Aluminium is all of this plus this. Now, oxygen has 8 electrons. Explain why the following electron in a box representation is high in energy. Now, wait, I think I missed something in this. Okay, yeah, I did. And it's asking us, state which electrons are free radicals. So a free radical is an electron that has unpaired electrons. So what I mean is, look, N here is 3 unpaired electrons. You have 3 electrons in its p orbital, but you also are missing 3. But we can't put these 3 because we don't have any more. So N is considered a free radical. Now Mg and Be, they filled their last energy level with the maximum it can be filled with. We can't say the same about Al though. Al is missing 5 electrons, so it is definitely a free radical. Or like it has an electron that's unpaired. Oh yeah, wait, what I mean is like here you have 3 unpaired electrons. Here you only have 1 unpaired electron. So if this box was filled, then it would not be considered a free radical. But since this box is not filled, or it doesn't have 2 in this box, it is a free radical. Moving on to the next question. So now oxygen, it has 8 electrons. Why is it high in energy? Now, this drawing is wrong because it's high in energy because this is not the ground state. Because like I said, according to Hund's rule, the orbitals must occupy the maximum number of unpaired electrons having the same spin before you start adding the other ones. So after all 3 of these have been filled with 3 ups, then you could start pairing the other electrons. So the lowest energy representation is supposed to be up, down, up, down, up, 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 then down. That's how it's supposed to be. Now, here they want us to write the shorthand electronic configuration. To write shorthand, you need to first write the long one, the one I just showed you. Fe is 26, I think. Wait, let me check. Argon is 18 plus 2 is 20. Yeah. Fe is 26. Chromium is it is 23. Copper has 29. No, wait, it's copper's. Let me check on my periodic table because now I'm calculating it. So copper is 29. I was right. So copper has of 29. Copper plus is copper plus is 28, but we'll talk about plus later. And we'll talk about Mn and copper later. Now we first write the full one. So it's 1s2. Let me make the pen a bit smaller. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d6. Now, after you wrote the full one, you have to look at your periodic table, Fe. The closest noble gas to it is argon. Argon has a charge of, it has 18 electrons. So you're going to count till 18 electrons. So 2, 4, 10, 12, 18. And you're going to group it up. And you're going to replace it. So you write argon in between square brackets. Then you continue 4s2, 3d6. Now for chromium and copper, there is an exception. Their d orbital, for chromium and copper, the d orbital, I'm going to write it here in red, d orbital for Cu and Cr can either be, or can either have 5 or 10. It's picky. It doesn't like having anything other than 5 or 10. So I'm gonna show you what to do if you have more than 5 or 10. So let's start writing the configurations now. Chromium, okay, it's 1s2, 2s2, 2p6, 3s2, 3p6. Now we reached 18. It has 23. So it has how many left? It has like 6 left, right? So now you're gonna write, let's continue with 4s2 and then 3d. You're gonna reach 3d4. Right? That's 6. But we said chromium cannot have 4 in its d orbital. It has to have 5 or 10. So what do? You take 1 from here and you give it here. You make that one 5. Now after you've done that, you group 18 electrons again, because the closest one to it is argon. And again, you replace it by argon and 4s1, 3d5. Copper is the same, but copper has 29. So it is 1s2, 2s2, 2p6, 3s2, 3p6, which are going to get grouped up in the end, because in these examples it's all argon, but it could be neon or any noble gas. Then 4s2, 3d9, which is copper, so it can't have 9. Again, it's going to steal 1 from here and give 1 till here, so it's 3d10, 4s1. It's going to become argon, 4s1, 3d10. Now for ions, you're gonna do the same thing as the thing above it. It's just after you have written it, you will look for your highest energy level. When I say highest energy level, I mean the number beside the coefficient. You will look for the highest coefficient and you will give or take from that one. Let me show you an example. So copper, I'm not gonna write it again. This is copper. So from copper, it's copper plus, so you have to take 1. What has the highest energy level here? The highest energy level is 4. So you're gonna take 1 from 4s1. 4s1 only has 1, so it's gonna become no. You're not gonna have 4s1. So for the copper ion, it's gonna be Ar 3d10. And that's the configuration for the ion. Let me write it down in blue. Ar 3d10, because we took 1 from the 4s. Now manganese is missing its 4s2, so it has, what's it called? Manganese has 3d5, so it's 25. So we're gonna write 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 3d5. 4s2, my bad. 4s2 3d5. Now mn is 2 plus. Again, you look for its highest coefficient, which is 4. You take away 2 from it because it's 2 plus. And then you group all of this up and as argon, and 3d5 you add it. So it is argon 3d5. Moving on to our next question. They're just telling us to complete the electronic configuration. They gave us up till 3p6. So then after 3p6 is 4s2, and then 28 minus 18 is 10. So it's 10 minus 2 again is 8, so it's 3d8. Now Fe3 plus is, you continue it, Fe is 26. So it is 4s2 3d6. You look at it as its highest energy level is 4. You take away 2 from its 4, it's gonna be left with no 4s, but you still need to take an extra 1. What do? You take it away from the next biggest thing, which is 3d5. And now you're left with this as your electronic configuration. Now calcium, they want the normal one. You just add 4s2. That's calcium. Now selenium 2 minus. You're gonna continue it. 4s2 3d10. That's 30. Now it is 4p6, 4p, whatever we're continuing, 4p and 4. Now here we have 2 in the energy level 4. Are you gonna take the S or the P? I told you take the highest, or you give to the highest. So selenium 4p4 is the highest. You give 2 to it, it becomes 4p6. That is it for that. Now question 18. Write the electronic configurations of SC and K. I'm gonna skip this because we did it up. It's just gonna be the same as calcium with 3d1. So, and this is gonna be like argon but with another one. Like, we should know by now how to do it. Give the possible electronic configuration of an atom X in GaX3, knowing that the ion of X has a full 3p outer shell. What does this mean? So they want you have an element that's GaX3. What does this mean? Let's revert it to its back, uncrisscross it, give them back. So it's Ga3 plus X plus, or X minus, sorry. Since it's X minus 1, it has to be in group. It has to be in group 7. It's in group 7, right? Yeah, it's group 7. So if it's in group 7, it must end with what's it called? It must end with 7 electrons in its last orbital. Since it's in group 7, it has a charge of 1s2. It told you it has a maximum full 3p outer shell. So it is 1s2, 2s2, 2p6, 3s2, 3p5. That, you're gonna say, why'd you stop? Because it's... Anyways, moving on. Here they're asking you to fill it out. You don't even need to know the element. Okay, actually you do. Chlorine is 17. So we have here 1s2. So it's up, down. Here it is 2s2. Up, down. 2p6. Or, well, it's... Actually, I'm gonna write in red the 1s2, 2s2, 2px, 2py, 2pz. And it's gonna be up, down, up, up, up. Sorry, up, up, up. down, down, down. Then here you have 3s2. It's gonna be up, down. And then you have 3px, 3py, 3pz. And since it's 17, so far, here you have 4, here you have 10, here you have 12. You need 5 more. So it's gonna be up, 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 down, down. That's it. Now next part is telling us chlorine gains 1 electron to become chloride ion. Draw the shape of the orbital to which it's added. Since we have only 1 left, here we can add it only, we can add it only here. So it's in the 3pz one. So we have to add it onto this axis because it is 3pz. And you're gonna say, why is it like this? Because we said p orbital has a dumbbell shape. It has to have a dumbbell shape. So yeah. Now compare the 1s orbital to the 2s orbital. Now they both have a spherical shape. Now I'm gonna say this by word, I'm gonna say it. They both have a spherical shape because all s orbitals have spherical shape. But the size within their principal energy, the size increases with their principal energy level. So 1s is smaller than the size of 2s, and it's a lower energy level. Now, chlorine tends to gain an electron and form Cl-. The shorthand electronic configuration would be Ne 3s2 3p6. You could do it, yani. Why is the chlorine atom considered a free radical? Let's draw chlorine. Up, down, up, down, up, 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 down, 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 up, down. We're gonna draw the atom, not the ion, of course. Up, 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 down, down. So now it has 1 unpaired electron. So it is a free radical. Now write the general form of Coulomb's law of attraction between charged particles that are as applied to lattice energy. They just want you to write Coulomb's law. Coulomb's law is energy equals a constant called K into Q1, which is charge 1, in times charge 2 over R. What is R? R is the radius or the distance between the centers of the charges. And yeah. Now there's another law of attraction with forces, but I doubt they're gonna ask, which is F equals the constant K, charge 1 times charge 2 over R squared. But that's for forces, so I doubt they're gonna ask us, but keep it in mind. Now here we have a photoelectron spectrum. Identify X and write its electronic configuration. Now when you're looking at this, it is very simple. It's just that this is 1s2, this is 2s2, this is 2p6, this is 3s2, and this is 2p. We need to find out. This is 1, this is 2. Okay, so this is 2p3. Okay? Sometimes they might give you 1s2 till here, so we know that this is 2 and this is 4. But here, no, each one is an increment of 1 electron. You're gonna say, how do you know that this is? Just memorize it. It's always the electronic configuration that shows here. Now, element Y is directly to the left of element X in the periodic table. Draw the 1s peak of element Y. I'm gonna draw it in red. The 1s peak of element Y is gonna be, what's it called? To the right of element to this one. So it's gonna be like most likely here. Or, sorry. It's supposed to touch the line. So that's probably the P1s peak of element Y. You're gonna say, why is it to the left of it? Now it's to the why is it to the right? Because element Y is a smaller atomic number, since it's to the left of the element X. So it has smaller number of protons. So it has a smaller nuclear charge. So it's gonna have a smaller binding energy. What's the binding energy? It's the energy that pulls the electron to the 1s electrons to the nucleus. So if you have a smaller binding energy, it's gonna like go to the right, because as you can tell, this is 1000, this is 100. So it's gonna go more, it's gonna decrease in binding energy since it's to the left of the element. Now, explain the photoelectron spectra below, which shows the amount of energy needed to remove 1s from N and from O. I think these are AP style questions, if I'm not wrong. So this spectrum shows that the 1s from N needs about a little more than, like, it needs like around 400 something EV to remove the 1s. Now for O, it needs around 550 EV to remove 1s from this one, because we're comparing the 1s peak right now. So we know that nitrogen is to the left of oxygen on the periodic table. Since nitrogen is to the left of oxygen, it's gonna require even less energy, like it has a lower binding energy. So oxygen atoms have a higher nuclear charge. Memorize this word for word, by the way. You should open the mark scheme later and memorize answers like this word for word. O atoms, or oxygen atoms, have a larger nuclear charge than N atoms. Therefore, you need more energy to remove the 1s from the O atoms, since they are more strongly attracted to the nucleus. Since O atoms have 8 protons. Oh wait, is it 8? No, sorry, I think it's 6. Yeah, sorry. No, it's 8. O atoms have 8 protons and N atoms have 7 protons. So O atoms have a higher nuclear charge, which means they are more attracted to the nucleus. If they are more attracted to the nucleus, you need more energy to remove them. Moving on, question 24. This is the photoelectron spectrum for neon. Explain the relative position of each peak and its size. This is the 1s2 peak, this is the 2s2 peak, and this is the 2p6. Is it 6? Yeah, it is 6. Now, the peak is very far here, like to the left from the second, like 2s2. It's because it requires much more energy to be removed than the 2s2. Like when you're drawing it, here's your nucleus. Here is 1s2, and here would be 2s2. It's a high jump in energy level. And then here would be 2p6. Okay, so the peak standing alone is for 1s2, and it's much farther because it's closer to the nucleus, requires much more energy. This one is directly close to the nucleus. It is the closest thing to the nucleus. It has the lowest shielding effect. Now the two other peaks that are close to each other are 2s2 and 2p6. Taller, of course, being 2p6, and they are almost the same difference from the nucleus, and their binding energies will be very small. So their peaks for 1s2 and 2s2 are the same height because they have the same number of electrons. So for this, they're literally just telling you, explain everything you're seeing in front of you in the diagram. What you're seeing is that 1s2 is the first one and 2s2 is the second one. They're the same because they have the same number of electrons. 1s2 is much stronger, has a much higher binding energy because it's way closer to the nucleus. 2s2 and 2p6 are much farther from the nucleus, and they have less binding energy, near to none. And 2p6 is taller than 2s2 because it has more electrons. And that is it for this video, because I'm only explaining chapter 1, and hopefully tomorrow chapter 2's video is gonna be out. Have a great day. Bye.